Alright, so continuing on with Chapter 7 is we have this fundamental theorem of calculus which says how antiderivatives, so remember that's what we've been doing, is finding antiderivatives, are used to calculate definite integrals exactly. So a definite integral is now where you're going to have an interval, and within that interval you want to find the area underneath the curve. So the calculations are based on this fundamental theorem of calculus. This is the big connection of direct integration. So the fundamental theorem of calculus, and we've talked about this before, says that if we have this function that's continuous on this interval a and b, then our big f of x would equal this integral of little f of t, and it has a derivative at every single point within this interval. Well, remember the reason why is because if this is continuous, I certainly can find the slope here, the slope here, the slope here, the slope here. And so if I differentiate this with respect to x, then basically what I'm doing is I'm saying, well, if I go from a to b, meaning this length of this interval, if I use the original function, meaning go back to the antiderivative and plug in these values, I can get exact area. So you're doing the same thing with derivatives. It's just now that we're saying we're going to get a number instead of a function. So if big F, f prime, the derivative of f is continuous, then we can do this by simply finding my integral from a to b of f prime of x dx. Now this kind of makes sense the way it's written, but the problem is in your problems, most of them are going to look like this, and then the original function they're going to call the big f of x. So that's my antiderivative, where this is the derivative. So it's a little confusing in the beginning, but once we keep doing these, you'll get used to it. So it's just saying then find the antiderivative, evaluate it at my interval points, and then subtract. I also see it written, well, let me go through, and so we're going to find, and then we're going to So again, this has given me exact area, where what we've been doing is drawing all those rectangles and approximating with the left or right hand able to find an exact area. The only issue with this is that you can only use this if you can find a formula, a function for the antiderivative. If you can't, then you probably are going to have to model the data and get something close. You know, if you need to, you actually. So basically what this is saying is if I look at this derivative here, 2x, okay, that's my derivative, and I find the antiderivative, then I can look at my limits of integration, plug those in, and get the area underneath my function. So my original function, in other words, this is saying my antiderivative would be, I could bring the 2 out front, I'm just looking right here. Remember, you're adding 1 and then doing that here to the bottom. So this would be 2x squared over 2, which would cancel and would just give me x squared. So this says from 1 to 3, 2x dx would equal f of 3 minus f of 1. Well, we just found f of x, so I just simply plug in 3 squared minus 1 squared, and that gives me my actual area. So that's all I'm doing, is I'm taking and I'm plugging these values into my antiderivative. Now notice that we kept saying over and over and over, but yeah, you have to really write, when you write this, it's really f of x equals x squared plus c. because it's a family of functions. There could be a constant. But notice if I go back in and I plug these into my x squared plus c, I'm going to get 3 squared plus c minus 1 squared plus c. And if you notice, because of that negative, my c's cancel anyway. And so we don't have to worry about when you have a definite integral, meaning that you have limits of integration. Now we don't even have to worry about the plus c part. So if I have something like this, I find the antiderivative. So the antiderivative would equal 6x to the third over 3, right? Because I'm just adding 1. And I'm going to evaluate that from 0 to 2. Well, I can rewrite that as 2x cubed and evaluate it 0 to 2. So that would be 2 times 2 cubed minus 2 times 0 cubed, which gives me my area. Oh, that's 16. If I look at this one, my antiderivative would be t to the fourth over 4. So from 0 to 2 would be 2 to the fourth over 4 minus 0 to the fourth over 4, which would give me 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16 over 4 minus 0, or just simply 4. Find this antiderivative. I can bring the 8 out front, so I'm going to kind of write this in a few more steps. So that would be 8x squared over 2 plus 5x, evaluating from 1 to 2, or 4x squared plus 5x from 1 to 2. So now I just simply plug in 2 for x minus plug in 1 for x. And if you do all the calculations, you should get 26 minus 9, or 17. All right, now this is that rule that if I have my antiderivative is going to be actually 1 over k to the ekt, where in this case my k is 2. So bring the 8 out front, 1 over 2, leave the e to the 2t, leave that alone, and I'm evaluating it from 0 to 1. So this is going to equal 4e to the 2t from 0 to 1. So this equals 4e to the 2 times 1 minus 4e to the 2 times 0, which is going to equal 4e to the second power. Well, notice this, 2 times 0 is 0, e to the 0 is 1, so I'd have minus 4. And of course this is something that you can throw into your calculator. Alright, this says write a definite integral to represent the area under the graph of f of t equals e to the 0.5t between t equals 0 and t equals 4. So that would be from 0 to 4, e to the 0.5t dt. Now I use the fundamental theorem of calculus to calculate the area. So this is my kt again, so this would be 1 over 0.5 e to the 0.5t from 0 to 4. And now I just simply, well, 1 over 0.5 is 2. And I plug in, sorry, that's an e. I plug in 4 minus 2 times e to the 0.5 times 0. And you should get something like 12.778. We can go back to our substitution that says that I look at the complicated piece. In this case, I'm going to let w equal x squared. So dw would equal 2x dw dx. And then dw would equal 2x dx. Well, notice I have the x dx, but I don't have a 2. So I'm just simply going to divide that 2 out, and this is going to be the piece that I substitute. So if I rewrite this kind of in the order so I can see it, times x times dx, notice that my x dx, I'm going to substitute this dw over 2. So I'm going to have from 0 to 2e, now x squared is my w, times dw over 2, which is the same thing. I can bring that dw over 2, that's just 1/2 out front. And so now I can find this antiderivative, which the antiderivative of e to the w is just e to the w, and my w was x squared, and evaluate it from 0 to 2. So I get 1/2 e to the 2 squared minus e to the 0 squared. I just plugged in these values, which gives me 1/2 e to the 4th minus 1. And of course you can put that in your calculator if you want to get an exact value. Now if we had something with infinite limits, either one or both the limits of integration is unbounded, meaning that we might have something that is going to infinity, well, what you could do is we could rewrite this. So let me first rewrite this as x to the minus 2 so we can see how to find the antiderivative. So the antiderivative is x to the minus 2 plus 1 over negative 2 plus 1, which would be x to the minus 1 over negative 1, which would be the same thing as 1 over x, and I'm evaluating this from 1 to infinity. Well, I can let b equal infinity, and so I end up with 1 over x. In other words, that's my b, my a and b. I plug in b minus I plug in my a. This gives me minus 1 over b plus 1. If I take the limit of this, meaning the limit as b goes to infinity, well then this fraction's getting smaller and smaller and smaller. Basically it's going to 0, so I simply end up with just 1. And C, just simply estimating large values for your upper limit, and you'd see what's happening is the area is actually converging to 1. So just another way to do it, except what we did first was more of a formal proof, and this is just proofs. And so as you can see, this is looking at this area here, okay, by computing this antiderivative.